determinant calculation. Okay. So matrix A, which is A, I'm talking about a square matrix. A1n, A21, A22, A2n, and A1, A2, A matrix size n by u. Okay. And we have to find determinant without remembering the adjoint and everything, and I will give you the formula which is based on the tensor calculus. And for the tensor analysis, one can actually, I won't discuss here how it will be, it is coming in the tensor calculus, rather I will be giving the final formula for the determinant of A, which is summation minus 1 whole to the power h, A1 K1, A2 K2, An Kn. Okay, that's only one formula, that's all. Simple, so simple. Entire determinant will be calculated. You don't need any cofactor, any adjoint, anything else. So now there are so many unknowns here. K1 to Kn, K1 to Kn, they are all varying between 1 to n, and no two Ki's are same, they are different. That means what? That means in this product, you see, this K1, K2 denotes different columns. I am saying K1 to Kn, they are changing. They are, see, if it is not that K3 equal to K4, they will be different. They cannot be same. K1 is not equal to K2, is not equal to K3, not equal to K4, and so on. Cannot be same. That means at a time, for each column, I will be taking only one element. I cannot have from the same column two elements here. Am I correct? Because K1, K2, Kn, they denote the column. If they are different, at a time, from each column, I will be taking different elements, so I cannot take two. And it makes sense if you look at matrix A, A11, A12, A21, A22. Determinant of A is very simple. We have seen earlier, which is A11, A22 minus A12, A2. And if you see that, for this product, it's like a product, right? So this product, you can see the first column one element is there, second column one element is there, right? Similarly, the first column, second column this is there, and this is the first column. So at a time from this set, only one will be selected. The same concept can be extended for the final formation of the n by n system, and in that case, only determinant factor is how this plus or minus will be. I am saying summation minus 1 whole to the power h. H could be 0, h could be 1, h could be 2, and so on. So first I will apply this formula for 2 by 2, and let's see how we can derive. So the original structure of this is 1 and 2. Okay, this K1 equals to 1 and K2 equals to 2, and the structure is like this. So, and how many terms will be there? There will be n factorial terms. There will be n factorial terms. So here the order of matrix is 2 by 2. So there will be 2 factorial terms here. So only 2 terms. For 3 by 3 matrix, 3 factorial. That means 6 terms. 4 by 4 matrix, it will be 4 factorial terms. 24 terms. 5 by 5 matrix, you know that. How many will be there? 120 terms. So that way we can see that any matrix we can even find out easily how many terms will be there. It is for determinant A calculation. For determinant of A, so now the way you can actually have the permutation between K1 to Kn, that will determine the numbers. So if you look at the permutation, there could be only 2 permutations possible. 1, 2, 2, 1. Permutation I am talking about in between K1, K2, Kn. How they do the permutation? Okay. So here permutation is possible 1, 2, 2, 1. No other way. No other way. And there is no repeat also. So there is no other way. 1, 2, 2, 1. So 1 is original structure. Okay. 1 is original structure. So if I replace it, okay. So in that case, number of replacement actually does matter. So if I replace, I will get this structure. So if I replace my h equals to 1 and h equals to 0. So h equals to 0 is the original structure. H equals to 1 is the one replacement from of the modified structure. It could be h equal to 2, 3 for the higher order matrices. Here you can have only h equals to 1. That means 2, 1 can be obtained by one replacement. How to replace? If I replace 2 by 1, you will get 2, 2, 2, 1. Right? Concept is clear? You are coming late. It's not allowed for next class onwards. So, determinant of A, first is h equals to 0, first modulus is the original structure. Okay? For the original structure, K1 equals to 1, K2 equals to 2. So, my minus 1 to the power 0, A1, 1, A2, am I correct? Second is plus minus 1 whole to the power 1, h equals to 1, second structure. A1, K1 is what? 2. A2, K2 is 1. So, you got A11, A22 minus A12, A21. That's it. Any questions, any doubts, confusions? Yeah. How the structure comes. So let's talk about the 3 by 3 system. So let's talk about 3 by 3. So 2 by 2 is quite clear to all of you. So let's talk about matrix A, which is A11, A12, A21, A21, A22, sorry, A13, A23, A31, A32, A32. Okay? Calculate determinant of A. So, first we have to structure K1, K2, K3, form a table. My original table is K1, 2, 3, first structure. Right? Second structure could be 2, 3, 1, for example. 3, 1, 2, 3, 2, 1, 1, 3, 2, and 2, 1, 3. Remember there are 6 factorial terms combination. Right? N factorial way you can arrange them, right? The permutation combination. So you have to do the permutation combination, very slight basics. These are the maximum ways 1, 2, 3, 4, 5, 6. 6 ways you can arrange 3 factorial terms. N natural numbers can be arranged in n factorial way. You have learnt it at plus 2. So as I said that my course requires only plus 2 mathematics. If you are very comfortable with plus 2 mathematics, we can do the job. And now you can have the h values. This is 1. Sorry, this is 0. The original structure. Okay. Next will be what? How many replacements? 1, 2, 3, 4, 0. How many replacements? Next. How many replacements? 2 or 3? 3, huh? 2 or 3 or 1? 1. White is 1. Somebody said 1. Somebody said 0 also. There are so many answers. 1, first bench. You don't know how to replace it. You didn't understand. It is not 1. How much it is? How much? 2. It should be 2. Okay. Why? So if you look at, so first 1, 2, 3 is there. So you can see the 3 is coming here. So if 3 comes here, so it will be 1, 2, 3. 3 comes here. So it will be coming like this, right? And then next transformation, we can get this one. So 2 steps. Replace slowly. No need to be in a hurry. 1, 2, 3. See, you are seeing 3 is coming first position. So 3 if will come, it comes, it has to be replaced by 1. Fill it up. 2 is still there. Then replace. What get the answer? Very easy. It's like a bookkeeping work. Okay, now it quickly. I don't want to discuss much of the steps. Next. All 1? All 1. Okay. Determinant of A. Give me the answer. First term. Quick. You will tell me the terms, I'll write the terms. First term. Input the sign, plus or minus. Input the sign. Plus, yes? Yes, who is volunteering? Yes, madam. Third bench, corner. Are you ready? Yes. Plus A11. Next. Minus because of minus 1 whole to the power. No, not minus. Minus 1 to the power 2 is what? Plus. Plus. Who can volunteer? Second term. Any hands, please? Second term. Any hands, please? I'm surprised you are not able to volunteer this. What's the problem? Second term is minus 1 whole to the power h. A1, K1, A2, K2, A3, K3. And K1 is 2, K2 is 3, and K3 is 1. Where is the problem to volunteer? It's so easy. What is that? A1? A1, 2, A2, 3, A3, 1. Next? Plus A1, 3, A2, 1, A3. Next? Minus minus A12, A13. No. A12 is first term, right? Which term? Which you are referring? Minus A13. Again minus. Minus is there, man. Minus A13, A22, A31, right? Yes. Please do not buzz. I am seeing blue shirt. Yes. You are hiding. No, blue. You are not having. You are having some yeah. The blue T-shirt. What's the problem, sir? I saw you talking. Yes, I saw you. Please do not disturb. Okay, it's not a fish market. If you think it's a fish market, then you don't come. You can go better to fish market. Don't get fish. Okay. Minus A1, A2, A3, 1. Next. Minus A11, A23, A32. Next. Minus A12, A21, A33. Over. That's it. So now you can see how easy it is, right? No need to remember determinant, formula, or adjoint, or cofactors. You may do mistakes. Anything you can do with this. Okay. So if possible, you can write a MATLAB module. You know, if you have any kind of extra time, you can write a MATLAB module to get the answer. Now for the 4x4 matrix, you can easily do it. 24 terms. Go home and do it. So now there is no nightmare to calculate determinant for the 4x4 matrix, right? It's so straightforward. Even 5x5 matrix, any matrix, if I give, you say yes, I can find determinant. This is the way, right? Okay. So next we will be talking about various properties of determinants, and we will be using this formula to derive various properties of determinant, which are very important and which will be useful for determining the solutions for the system. Okay. Properties of determinant. Determinant of A equals to determinant of A transpose. Determinant of A equal to determinant of A transpose. How to prove it? Using this formula, remember that. You have a formula here. You have a formula here. What to write determinant of A? First property. Determinant of A is nothing but summation minus 1 whole to the power h, A1 K1, A2 K2, and AN Kn. Right? Correct? Okay. Now, determinant of A transpose will be what? From this formula, AK1, yes, AK11, AK22, and AKN. Okay? So now you can apply method of induction. Okay? You can say that, okay, by n equal to 2, what actually happens? In that case, you see that this 1, 2, n, they are all different now. It's quite obvious here. That means at a time, from each column, I am selecting only one element. Okay? Another terms will be there. So that was the criteria. At a time, you should be picking up one item from each column, and here K1 to Kn. So basically, what you are saying that I am getting the product of all possible cases where I am picking up the item from each column, and this will be the same here because we are just doing flipping of the sign, and you can see that K1, K2, they are varying between 1 to n, and here it is 1 to n. And these numbers are the all possible numbers which are actually available. Okay, that means this thing is such that at a time you are not picking up the same row, same element from a row. That means if you say 1, 2, 3, 4, a particular term cannot be multiplied like this 1 and 2 because you are not picking up the same row. Why you are not picking up the same row? Because if you look at the determinant formula, which is A1 K1, A2 K2 for this case, and if you see that 1 and 2 they are different, that means you are not picking up the same row. You are picking up from different row. So at a time when you pick up the element, they don't belong to the same row or same column. Okay, they belong to different row and different column. So same thing here also. They don't. So here, so if you look at K1, K2, Kn, all are non-equal. And how you get all possible combination. So the number of combinations, the nature of combinations will not be changing. They are same. That's why determinant of A equal to determinant of A transpose. Any questions here? Any doubts? Any questions? Any doubts? Any questions? So I can explain again. Again, okay. So if you look at this example, which is here the determinant of A is how to calculate for 2 by 2. Determinant of A, which is A11, A22, K1, K2 minus A12, A21, right? What you are saying that when I select, this is A12, A11, 12, 21, 22. If I am selecting the first column and this is the second column and they don't belong to the same row, similarly these two are also. Okay? Correct? So what we are finally getting, if you just flip it, what I did, I flipped it. 1 2 will become 2 1, 2 1 become 1 2. Okay, it is not changing, no? That's what I am doing, and that's what the determinant of A transpose. Okay, I do the same thing for the 3 by 3. This A matrix, A transpose, A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay? Understood? And if you look at, if you flip this, that means the first term is okay. Second term is A21, A32, A31. Sorry, A21, A32, A13, right? Okay, and this will be the same. Okay? This sign, if you look at it, will be same. It will be different. So you have this, when you do at A21, A21 is there? Yes? The third one, A21, A32, A13. Same sign, sign not change. So like that you can actually explain. So what actually I am saying that this pattern will not change, the same number of things it should be there, and this will appear in the same format. I think next we will go to the next term. So next will be determinant of A bar, determinant of A whole bar. Let's talk about that one, second property. Second property. Determinant of A bar, which is determinant of A, sorry, again you write formula, determinant of A. I will omit A bar is now onwards written as A, because I don't want to write all the time A double bar. I am just writing A bar. In lieu of A double bar, I am writing A. This is always better. This minus 1 whole to the power h, A1 K1, A2 K2, and A K. And you know that in complex quantity, alpha 1, alpha 2 bar is nothing but alpha 1 bar, alpha 2 bar. In complex quantity, the complex algebra you have done, alpha 1, alpha 2 bar, if you take the complex conjugate, nothing but the complex conjugate of alpha 1 bar, alpha 1 and alpha 2. So alpha 1, alpha 2 bar is alpha 1 bar into alpha 2 bar, right? Okay, that means what? That means if you just take the bar, if you take the bar and if you take the individual element, you get the same thing. So it is like one step process. That means what I am saying that alpha 1, alpha 2, alpha n, if you take the whole bar, alpha 1 bar, alpha 2 bar and alpha n bar. If you apply, you get it. Right? Clear? Yes? Yes or no? Clear? Okay. Third property. Very interesting property. If A has a row or column 0, determinant of A is 0. This kind of things you are just seen, but this is a different way you are actually proving it. Third property. Third property, if A has a row or column 0, determinant of A equals to 0. If A has a row or column 0, determinant of A equals to 0. How to prove it? Remember, A has a row or column 0. I am assuming column 0. Okay? And then how to prove it? If it is a column 0, if you take the transpose, it has row 0. Right? And determinant of A equals to determinant of A transpose, in that you can prove it. So better to assume that A has a column 0. So if I am assuming my jth column has zeros, jth column. So determinant of A, which I can write as summation minus 1 to the power h, A1 K1, A2 K2, AI Ki, AJ Kj, AN Kn. And now you can see that from Kj, at least one element will appear in all the terms. But and those elements are 0, so the determinant of A equals to 0. So easily you can prove it. Without this formula, it is very difficult to prove. So that's why this formula is so powerful. You can prove anything so determinant with this formula in one step. Clear? Shall I go to the next one? Next property. When the two rows of A are interchanged, please write down. When the two rows of A are interchanged, determinant A changes sign. When the two rows are interchanged, determinant of A changes sign. That means it will be minus what is determinant you are getting. So the two rows are displaced. The two rows are displaced. Determinant of A will change the sign. So assume I and j rows are replaced. So my initial formula of determinant of A is minus 1 whole to the power h, A1 K1, A2 K2, AI KI, AJ KJ, AN KN. And I am saying that my I and jth row are replaced. Okay. So I am getting new matrix A prime where I and j rows are replaced. Right? So what did you get the formula from here? Determinant of A prime minus 1 whole to the power h, A1 K1, A2 K2, and here we will get AJ K, yes, AI KJ, AN KN. Right? Next step. Now what we have here? We have K1, K2, Kn, where you have Ki and Kj. So if we can replace one replacement, what you get? A1 K1, A2 K2, AJ KJ, AI KI, AN KN. Right? So we'll get minus 1 for a particular term. So we can say that one term of determinant of A prime, we have the sign problem, that is the original structure is this one. So we have A1 K1, A2 K2, AJ KJ, AI KI, AN KN. Why minus for this particular term? Because of the one replacement. So like that each term will have the minus sign change because of this replacement. So the determinant of A prime should be having minus 1 whole to the power h into minus 1. I can write this formula, and this is nothing but minus 1 summation minus 1 whole to the power h, A1 K1, A2 K2, AJ KJ, AI KI, AN KN. Forget about the order, but the same terms, but the determinant of A, AI KI, AJ KJ, doesn't matter 2 into 3 or 3 into 2, both are same. Okay, so it is nothing but minus determinant of A. So you see that if one row has been interchanged, determinant of A prime is nothing but determinant of A. Steps are clear. Any doubts, please ask me. Steps are clear? Yes? Steps clear? Will you understand the step? Okay? You have to apply the one term and then you directly got minus 1 here, and then this term is unchanged of determinant of A, and this minus of determinant of A, and that's it. So if one row has been replaced, 2 rows different issue, 3 rows different issue, we can do case by case basis. Okay? But if one row is replaced, definitely it is changing sign. This kind of things we have done in the plus 2 algebra or something, or we take first level mathematics. I don't think I have proved this way, right? It has not been proved this way. Okay, shall I go to the next property, or here any problem? Next property shall I go with? Any question here? No question, everything is clear? Okay, now I go to the fifth property. If the rows or columns are identical, if the rows or columns are identical, then determinant of A equals to 0. How to prove it? If the rows or columns are identical, same way. I and J, I am talking about column. Column is easy to visualize here. Row is difficult because you are always talking about the column. I replace I, here we have replaced the row. We can actually take rows also, no problem. Any rows, any columns, no problem. I and J rows are replaced. What actually happens? They are saying, what actually happens? What will you get? Can you prove it from here? You have done it. Who can volunteer? How to prove it? Determinant of A equal to 0. No idea, first bench? Yes, how to prove it?
Sir, actually, if the rows and columns are interchanged,
Not, I just talk about rows. Not rows and columns. 2 rows are interchanged. Or 2 columns are interchanged, right?
then that A is not changing. So that A plus that A dash is 0.
Pardon?
That A plus that A dash.
Not that, determinant.
Okay.
Be determinant. Don't be in shortcut.
Okay, sir.
Yeah.
Determinant of A plus determinant of A dash is 0.
Not A dash. Determinant of A equals to minus determinant of A. Right? Equals to minus determinant of A. Because if you change it, nothing will actually matter.
Yeah.
Okay? So you will get determinant of A equals to 0. 2 of determinant of A equal to 0, determinant of A equal to 0. Is it clear or not? Is it clear? I am replacing the 2 rows here. I am replacing the 2 rows here. But the entries are identical. Doesn't matter. Even after replacement, we can see the same effect. So in that case, determinant of A equal to minus determinant of A. The same effect. Okay? So it has to be, so what actually happens, it has to be 0. If determinant of A equal to determinant of minus A. It has to be 0. So if you are not able to visualize, so applying this you can get it. If you are not able to visualize, you can take 2 by 2 or 3 by 3 system. Okay? For your choice and get the answer. Or you want to derive this one? I think you can go ahead at home and do it. If any problem, I can do it in the class. Okay? Next, very interesting. If all the elements in a row, are multiplied by alpha, if all the elements in a row are multiplied by alpha, the determinant is multiplied by alpha. 6th property. Sixth property. If all the elements in a row are multiplied by alpha, if all the elements in a row are multiplied by alpha, the entire determinant is multiplied by alpha. Determinant of A, which is summation minus 1 over to the power h, A1 K1, A2 K2, AI Ki, AN Kn. I row, I am saying it is multiplied by alpha. Okay. So if I have determinant of A prime such that its ith row is multiplied by alpha, and this term will be coming only once, right? So I can take it out. Alpha minus 1 over to the power h, A1 K1, A2 K2, AI Ki, AN Kn, and it is nothing but alpha determinant of A. So each row, if one of the rows is multiplied by alpha, entire determinant is multiplied by alpha. So now we see that with this we can actually, one or two steps we can get in the answer. I think if you go by adjoint and all those things, a long procedure. I don't remember though all this procedure. If you could remember, you can appreciate this method better. Seventh property. If rho j is multiplied by alpha, please write down. If rho j is multiplied by alpha, which is not equal to 0, if rho j is multiplied by alpha, which is not equal to 0, and added to rho I, the determinant is unchanged. This type of things are actually there earlier. This kind of proofs. If rho j is multiplied by alpha, which is not 0, and added to rho I, the determinant is unchanged. The determinant is unchanged. You got the point? What I said? Okay. So determinant of A, which is summation minus 1 to the power h, A1 K1, A2 K2, AN Kn, forming another matrix where the rho j is multiplied by alpha, minus 1 to the power h, A1 K1, A2 K2, rho j is multiplied by alpha, and which will be added. That means I should write AI Ki plus, also it will be there. Am I correct? Does it make sense what I wrote? Yes or no? Does it make sense? Okay. So if we look at, if it doesn't make sense, I'll give one more steps. Now you can see that rho j is multiplied by alpha added to AI Ki. So AI Ki will be modified as AI Ki plus alpha Aj Kj. Aj Kj will still be there. Right? So what is the step now? Next step? Next step will be minus 1 whole to the power h, A1 K1, A2 K2, AI Ki, I can split out, Aj Kj, AN Kn plus alpha summation minus 1 whole to the power I, A1 K1, A2 K2, Aj Kj, Aj Kj, AN Kn. Two rows are identical, right? And we have found that that in that case this determinant discontinuation is 0. Okay? We have just found. So what is it? So this is nothing but original determinant. So determinant is unchanged. This is nothing but ordinary determinant definition. A1 K1, A2 K2, AI Ki, Aj Kj, AN Kn. So it is nothing but determinant of A. Any doubts? Any confusion here? Any doubts? I am not hearing any doubts. This is a right time for to clear the doubts. Otherwise, the exam this kind of questions will be coming. Questions? Everything is clear? Clear. Okay. Number 8 property. If A is upper or lower triangular matrix, this is a very interesting property. If A is a upper or lower triangular matrix, then determinant of A is the product of all diagonal elements. If A is upper or lower triangular matrix, if A is upper or lower triangular matrix, if A is upper or lower triangular matrix, then determinant of A is the product of all diagonal elements. So let me repeat once again. If A is upper or lower triangular matrix, then determinant of A is the product of all diagonal elements. Okay? So property number 8. first, whatever you do, first write the property, our definition, determinant of A, which is summation minus 1 over to the power h, A1 K1, A2 K2, An K. Okay? Upper or lower triangular matrix. I will just do first for upper triangular matrix. For upper triangular matrix, how does it look like? A11, A12, A1n, 0, A22, A2n, 0, 0, A33, A3n. So below the diagonal, everything is 0, right? So for upper triangular matrix, what will happen? Aiki equals to 0 when? Equals to 0 when? If not equals to, and I not equals to k means it's coming, no? I is greater than k, yes sir. I is greater than k, right? Yes. Yes, I is greater than k. So what actually happens? What actually happens here? How many terms will be there from here? There are so many terms, so the only one term will exist, other terms will go. Because you look at A1, K1, it will be non-zero if K1 equals to 1. Okay? Then K2 is 2, 3, has to be 0 because of this formula. Other terms will be all 0. Okay? Now A1, K1, if K2 equals to 2, okay, A22 is there. If K3 is there, A33 is there. If you flip something, some terms will be 0. So only this term will exist if K1 equals to 1, K2 equals to 2, Kn equals to n. Otherwise, you see some of the terms will be having this and they will be 0, and one of the terms in a product is 0 means the entire product is 0, and only one term will exist, and that's why determinant of A is nothing but the product of diagonal. Okay? So you can prove it. So I may ask in the exam, prove it for 3 by 3 matrix. So this is where I'm doing. So what actually happens that, you know, if this product will exist if I is less than k. Okay, but if I is less than k, sum of the i's it will be greater than k, right? It has to be. And in that case, those terms appear means they will be 0. Entire determinant will be 0. Only the term will remain, which is A11, A22, A33, An. Last property number 9. For identity matrix, determinant is 1, which is very straightforward. For identity matrix, show that determinant is 1. So determinant of identity matrix of order n is 1, which can be proved from property number 8. Now I'll be picking up some of the assignment problems. If you have the assignment, you are supposed to bring assignment. Bring the assignment. No. That's what I'm saying, It's not the assignment, it is not there. Problem set 1. Okay. If this is not there assignment, that's fine. I will keep some problem here. Find determinant 1 plus C1, 1 plus C2, 1 plus C3, 1 plus Cn. Can you find determinant? And I can say that the answer is C1, C2, C3 up to Cn, 1 plus 1 by C1, 1 by C2 and up to 1 by Cn. do that? How to prove? Think about it. If you can use all 9 properties. Okay? I'll pick up another problem. Okay? So this is for home task. Think about it. Using 9 properties, if you can simplify this determinant. For example, we have seen that if you multiply jth element by alpha, add with the ith row, determinant will not be changed. So these kind of operations if you can do, get a simplified matrix like diagonal element or something, and can you get this kind of expression? Okay, I will pick up another one and just give you the hints how to do it, and then next class I will be doing different topics. So this I will finish it here. Next, another problem I will just show you. Dn equals to x1, 1x, 1, 1 and x. The answer is x minus 1 whole to the power n minus 1, x minus n plus 1. Determinant. What you can do that, I'll give you the hints here. First row, if you subtract the last row, what do you get? X minus 1, 0, 0. Okay? Similarly, will that be changed? Determinant will be changed if you subtract a row from another row? Of course not. You have seen the property number 6 or 7. If you add some row, nothing will change. Okay? And alpha could be 1. So, similarly, you subtract this from this, you will get what? 0, x minus 1, 0, and this. So, finally, what you will get? You will get upper triangular matrix. And if you get upper triangular matrix, diagonal elements will give the determinant. So, I apply all the properties and do the determinant calculation. Thanks for attention. Next class will be on Friday. Alright? So, see anything we have fixed next week? 4:45. Next Wednesday. Special class.